And if we finish up this part, which I think we will, I'll have to decide what I do Monday and Wednesday. Probably for sure need to begin part 5. So let's just see. All right. So yesterday in lab, you guys did strong acid with a strong base and a weak acid with a strong base. And in this part, we already talked about the chemistry behind dripping in a strong acid to a strong base. Now we need to see what the chemistry was like. And you guys did, this exact same thing, acetic acid, sodium hydroxide. It formed sodium acetate, which is your salt, and water. So what sort of chemistry was going on? Well, here is the balanced equation. And we're going to do 3 different points of the titration and kind of think through it. So what I'm going to do is take this 25 milliliters and 0.1 molar CH3COOH. I'm going to put it here. So 25.00 milliliters, 0.100 moles per liter. And our sodium hydroxide was 0.100 moles per liter. And our volume for sodium hydroxide is going to be what varies. So we're going to do this at 3 different points. We're going to do it 20 mils of NaOH, 25 mils of NaOH, and then 30 mils of NaOH. But before we kind of jump into it, let's double check where the equivalence point would be. So the stoichiometry is a 1-to-1 relationship between the acetic acid and sodium hydroxide. They are both the same molarity, and because of that, then the equivalence point for NaOH will be at the same volume of as your CH3COOH, your acetic acid. So does this make sense that your EP equivalence point will be at or equals to or at 25.00 milliliters of NaOH? And actually, it's important to know when your equivalence point is. Notice that the three volumes we're going with, this one is at EP, at equivalence point. This guy right here is before equivalence point, and this is after equivalence point. They will have 3 different chemistries going on. So again, the pattern what we're looking at is a WA, weak acid, is what your CH3COOH is, and SB, strong base. So this will be characteristic of this sort of titration. So before the equivalence point, 20 milliliters. At that point, what has happened is that you have converted some of your acetic acid into sodium acetate. So let's see, how do I want to do this? So we're going 25.00 milliliters. That was what we have in our beaker that we're titrating into. It's 0.1 molar. And this point we have 20.00 milliliters, and it's also 0.1 molar. Okay. For every little drop of strong base is going to react with your acetic acid. So this is going to be all gone, all used up. And can you see where you're going to have some of this remaining, some left? Okay, some of your weak acid is left. And then you will have formed this over here. Now, what this over here is CH3COO minus. What that thing right there is that is your conjugate base of your CH3COOH. So you can see here that what's described, actually you have created, not a monster, but you have created a buffered solution. So you have some left, CH3COOH, and you have you've created some acetate by dripping in a strong base. So we basically, pun intended, need to go at it and find out, we'll probably go for moles of acetate formed and moles of acetic acid remaining and plug it into the Henderson-Hasselbalch equation. Anytime you see buffered solution, you should be thinking HH equation, which is exactly what we're going to do. All right, so let's count beans. So let's keep it in millimoles instead of moles. It's just easier. So we can get to millimoles of the acetic acid we started out with by taking the volume, 25 milliliters, and multiplying it by the molarity, 0.100 millimoles over 1 milliliter. And that will give us 2.50 millimoles of CH3COOH. They're dribbling in. You're not going to get the good chair?
I don't want to make like a loud noise because I didn't want to interrupt, but I guess I already can.
Oh, you can. So what was the printer was acting up?
He was printing off 15 copies of a 7-page paper. I was behind him.
What?
Yeah.
You should get your comfortable chair. You just don't look right, Jacob. Did anybody see Lindsay? Okay. Okay. So this is the millimoles we're starting out with. Okay. So all of the NaOH I said was gone. So all of this is going to actually convert the sum of the CH3COOH to its acetate, the CH3COO minus. So we need to know how much at that point in titration of NaOH we added. So we had 20 milliliters, so 20.0 milliliters. Over the molarity, we were given 0.100 millimoles of NaOH per milliliter solution. So that gives us a 2.00 millimoles of NaOH that we've added. So how much of the acetic acid has reacted? Well, we can use the 1-to-1 stoichiometry. So don't skip this step. It's tempting. So it looks like this. We have 2.00 millimoles of NaOH times 1 millimole of CH3COOH over 1 millimole of NaOH. And you're right, that says that we're going to use up 2.00 millimoles of CH3COOH. So now you know what we're going to do. We're going to subtract that amount from the 2.50 that we started with. So millimoles of CH3COOH remaining would be 2.50 minus 2.0, which is 0.50 millimoles of CH3COOH. So we're getting ready to plug some numbers into the Henderson-Hasselbalch equation. Don't be fooled, okay? This guy right here, that is not going to go into the HH equation. That's your strong base. The thing that's going to go into the HH equation, we still have to come up with. It's going to be the CH3COO minus. So it looks like this. So how much of CH3COO minus would have formed? Well, it's 2.00 millimoles. But how? We're going to use stoichiometry, 2.00 millimoles of NaOH, and use the stoichiometric ratio, 1 millimole of CH3COO minus for every 1 millimole of NaOH. And yes, you're right. We get 2.00 millimoles of CH3COO minus. That is going to be the base in your HH equation. Oh, did you see I did? Base in HH equation. Okay. Now I think we're almost ready. Remember, the Henderson-Hasselbalch equation goes like this. It's a buffered solution, and you can knock out the pH. You need to know the pKa plus, it's going to be always the ratio of base to acid, so the conjugate acid-base pairs. So we're going moles here. So remember then that our base is the CH3COO minus, our acid is the CH3COOH. So we need to go and look up the Ka of CH3COOH, so that should not be a problem. It's a problem, or it becomes interesting, an extra step, if it's not if the weak acid is if the weak base is predominant. So this is the Henderson-Hasselbalch equation. And we're going to go with number of moles instead of molarity. And it looks like you're just going to have to take my word for this, okay? If you were to go for acetic acid and find out its Ka and apply the P function, negative log of that, you get 4.74. So I think we probably did it in our notes earlier somewhere. So that's the pKa plus log of the ratio of moles of base, which that's our acetate, that's CH3COO minus, the moles of acetic acid remaining, 0.5. So when you plug that into your calculator, hopefully you'll get 5.34. So that would be the pH at that point in the titration. 5.34, 20 milliliters of sodium hydroxide. 3 regions. This is before the equivalence point. You get a buffered solution. And in this case, we are titrating a weak acid with a strong base. It would be the same thing if we had a weak base with a strong acid. Same chemistry. Okay, so the next titration point is at the equivalence point. Now, at the equivalence point of a strong acid and strong base, it was neutral. At the equivalence point of a weak acid and a strong base, it's not neutral. What's happened at the equivalence point is this is all gone, all gone, all gone. But what's not gone is this guy over here, CH3COO minus. So that's what's driving the pH. And one of the things CH3COO minus acetate is good at doing, if you look at it, you're like, I don't think it can donate a proton, but I think it can accept a proton, and you'd be right. So what that looks like is, and you're going to see it here in a minute, CH3COO minus acetate can react with water, and it's in equilibrium to form acetic acid plus OH minus. Basic? Yeah. So this thing's going to be basic. And what we've been talking about is that's where our Kb comes from. Kb is in this case, be CH3COOH. Also in the numerator, we have OH minus divided by CH3COO minus. Okay, so that's kind of what's going, actually what I just put on the board, you're going to see here in a minute too. But all the reactants are used up. That's by definition what a equivalence point is. And we have an acetate that is actually doing this with water to make it basic. So the resulting solution is a dilute solution of the conjugate base of a weak acid. The conjugate base of a weak acid. Conjugate base, weak acid. So the pH should be higher than 7. So let's do some work and see what that looks like. So the millimoles of NaOH added, we said was 25, and its molarity was not the millimoles of NaOH added. The volume of NaOH added was 25.0 milliliters. Its molarity is 0.100 millimoles over 1 milliliter. So you're back to the 2.50 millimoles of NaOH added. We can double check that the millimoles of CH3 remaining, if it's at the equivalence point, it should be all of it reacted. Let's see. For the, 2.50 millimoles of NaOH has a stoichiometry of 1 to 1. 1 millimole of CH3COOH per 1 millimole of NaOH. Yeah, that gives you 2.50 millimoles of CH3COOH that reacted. And now we can actually, a few slides ago, we came up with the millimoles of CH3COOH you had initially, and it was that same number. So remaining is 2.50 minus 2.50. So yeah, you're at the equivalence point. Okay. So, all right. So how much of that acetate did you form? Excuse me. Again, using stoichiometry based upon your 2.50 millimoles of NaOH you dripped in. Stoichiometry is 1:1, so 1 millimole of CH3COO minus per 1 millimole of NaOH. So yeah, you form 2.50 millimoles of acetate, CH3COO minus. This seems a little belabored to me, but maybe it's just. But now that, finally, is something we're going to have to use. That's what's driving your pH. So in order to get to the hydroxide ion concentration, does this make sense? We're going to actually end up with an ice table. And in our ice tables, it's never about moles, it's about molarity, which is moles per liter. So what's our volume at that point in the titration? Do you think?
Is that the equivalence? Or is
No,
that
the volume.
gas?
So basically, what acid we had and what base we have now. Anybody? What was the volume of acid?
25 milliliters we started out with, and at once it's 25 milliliters of base, so it
So-
would be 50 milliliters of solution.
Yep, that's it. 50 milliliters of solution. You got it. That was what I was after. Perfect. So brackets means molarity. We have to come up with the molarity of the CH3COO minus. So we'll calculate that by taking that 2.50 millimoles of CH3COO minus divided by the 50 milliliters of solution. And we'll go with 3 sig figs, so 50.0 milliliters. I can almost do that math. Well, maybe not. You end up with 0.0500 molar. That's the molarity of your acetate ion. And so here's one where, and it seems like so long ago, but we did these problems where you know the initial, or is that the final? You know the molar concentration of CH3COO minus, and we know the Kb. We can figure out the Kb. Another drama. So what is the pH of this molar solution of that conjugate base, that weak base? So this right here is what I put on the board earlier. So what is that base going to do? It is going to abscond onto a proton or a hydrogen from a water molecule, and what that's going to do is leave it basic. It's going to form acetic acid, it's conjugate acid. We could write the equilibrium constant expression, the Kb expression looks like this. It's the same thing as this up here, where we have the acetic acid times the molar concentration of hydroxide ion divided by the acetate ion. And again, I feel like I'm skipping a few steps to show you, but hopefully you can go back in your notes and find out how I got the Kb. Actually, the Kb came from the is equal to Kw divided by Ka to get the Kb. All right. Oh, maybe I'm going to show you here. So where that Kb came from is here. We can't look up the Kb for acetate on a table. It just doesn't exist. But we do have the Ka for acetic acid. So KBs are KW divided by KA. In this case, 1.0 times 10 to the negative 14 divided by 1.8 times 10 to the minus fifth, giving it 2 sig figs. Like you saw a minute ago, the KB is 5.6 times 10 to the minus 10th. It's kind of a backdoor into something that's not on the table. Cute shoes are on there. Your whole outfit's cute, though.
Thank you.
Okay, so here's our ice table. Like I said, it feels like so long ago. The initial concentrations across the board, we're assuming you're starting out with 0.0500 molar of your acetate, nothing of your acetic acid, nothing of your hydroxide ion. If we let the change be equal to the amount of the moles of the molarity of CH3COOH that reacts with the H2O, or excuse me, yeah, H2O, it looks like this. We have a minus X for our CH3COO minus, we have a plus X for our CH3COOH, and a plus X for our hydroxide ion. What we know then is at equilibrium, we take the initial and apply the change, so it looks like this. So at equilibrium, for your acetate ion, you're looking at 0.0500 minus X. At equilibrium, you have X moles per liter for your acetic acid and your hydroxide ion.
Is that usually a simplifying
Yes,
assumption?
we're definitely going to use a simplifying assumption. But if we were to substitute these in without the simplifying assumption, this is what it would look like. So this is substituting those equilibrium concentrations in for our KB expression. The reason we need to do our simplifying assumption is we would end up with an x squared value, our value associated with an x squared. We don't want that. So the simplifying assumption is that if x is pretty darn small, in this case compared to the initial concentration of the acetate ion, 0.0500, okay, if it's way small, then if you subtract something small from 0.005, you get 0.005. Sorry, not 0.05. If you subtract something small from 0.05, you get 0.05. So this denominator essentially becomes 0.05. And life just got a lot easier. So if we rewrite it, okay, it's on the next slide. And this is, remember, I messed this up a few lectures ago, but the way this works is if you take the molar concentration, which was 0.05, and if you multiply it, wait, no, that's not, I'm turning wrong. This one. If you take the KB, which is 5.6 times 10 to the negative 10th, times 100, okay, that's 5.6 times 10 to the minus 8. Okay, that needs to be less than, in this case, 0.050. And that is true. So that's how that works. So after we apply the simplifying assumption, this is what our equation becomes. X squared divided by now 0.0500 is equal to KB, 5.6 times 10 to the minus 10th. Kind of cross multiply and take the square root of it. So you need to take the square root of 2.8 times 10 to the minus 11. And you end up with 5.29 times 10 to the minus 6. And that would be moles per liter. And then make sure we're after pH, so we're not quite done yet. So what that is associated with is that is the molarity of your hydroxide ion. So you need to kind of do some of the skills you did before to get the pH out of that. A couple ways to skin this cat. So if that's our hydroxide ion concentration, see which way I did. Yeah. So we could get not the pH, but the pOH by applying the P function. So if we take negative log of 5.2 times 10 to the minus 6, you'll get a pOH of 5.28. Then how do we get pH?
Subtract from 14.
Yep, subtract it from 14. So pH is 14.00 minus 5.28. That's a lot of work to get the pH at equivalence point. So your pH, now it should be basic, and it is. Your pH is 8.72. And that's at the equivalence point just because your acetate ion is driving your acetate ion is driving the pH of the solution. And I can't remember in my notes. Let's see. Okay, so we did 20, we did 25, and now here's 30. So 30, we're after the equivalence point. So 30 after the equivalence point, of course, that's gone. Okay, and we have this forming. But after the equivalence point, we have this in excess. And actually, it's the sodium hydroxide in excess that's going to make your solution basic. After the equivalence point, you have excess base added. And actually, I thought that's what I did. After that, see. If you want to go back to the HCl NaOH calculation, that's this. You'd have the same chemistry going on there at 30 mils of titrant as we do here. So I don't do it for you here. All right. So this might be kind of what, now your molarities were different, but this actually is what you guys did yesterday. You had the pH meter going, and then at certain volumes, you stopped, took the pH, and put in the volume. So this weak acid being titrated with a strong base, this is kind of what this is what your data would look like. And the middle column is the millimoles, or the moles, not millimoles, the moles of NaOH added. So hopefully your curve is going to look kind of something like this-ish. Okay, and like I said in lecture, or in lab, pre-lab, what you're going to be looking for is where the straight part is, halfway where the straight part is. That's what we call the inflection point. So if this is the equivalence point, we go down here, this 25 milliliters is the equivalence volume. See how that works? And you can see we did this calculation. Remember we said, we just did it. We said, what is the pH? What was it, 8.62 or something like that? The pH when you have 25 milliliters of NaOH added. But the other thing is, I'm looking at it, can you see where this looks very similar, similar to, the strong acid HCl and the strong base, the last part of it. And that's not on accident. All right. So calculation 4 is this question for your lab write-ups. The half neutralization point. And I tried to kind of show you, I'll go back here. Half neutralization point looks like this. If this is the full neutralization, the half neutralization point would be what, 2.5 milliliters. Does that make sense? 12.5, excuse me, 12.5 milliliters. That didn't make sense to me. So here's 12.5. So I would go up here, that's the half neutralization point, and then I would go over here, and that's the pH at the half neutralization point. And like I told you, and it's going to say on the next slide, at that point, the pH is equal to the pKa. So let's kind of see why that would be. we said, and if you're at the half neutralization point, you are doing what I just described. You are creating a buffered solution, okay? So if you're creating a buffered solution at the half neutralization point, you have, let's use the example, we have half of this left, and we have formed, I don't know how to say this, we have formed half of this that's going to be formed. Okay, so the thing is we have equal amounts. Equal amounts. And if you divide things that are in equal amounts by each other, guess what? You get 1. That makes sense? You have equal amounts. You have equal left and equal form. Okay, so those quantities divided by each other gives you a ratio of 1. And in log base 10 of ratio of 1, sorry, oh gosh. Log 10 of 1, log base 10 of 1 is 0. Log of 1 is 0. So if that's 0, then pH is equal to pKa. Kind of fun. Okay. So just kind of follow up with a few things. One, in the 2 titrations we did for this part, I kind of tried to go at the very front end and say, well, what is the equivalence point? Okay, where I kind of put the molarity volume, I put molarity, question mark volume, find the volume. It's important that you know the equivalence point so you know what the chemistry you're going after. But they're not always so obvious. So let's take a look at this one. So you could run into this on your test on Thursday. Let's see what we got. And in Chem 1, I said I'm all about taking these volumes and molarities and putting them underneath the species they apply to. So the CH3COOH, I'm going to put 35.0 milliliters, and I'm going to put molarity of 0.108. And then, let's see, under my NaOH, I'm going to just simply put a molarity of 0.235. And in Chem 1, I put question mark volume. And that question mark volume, that's your equivalence volume. That's your equivalence point volume. So, you know, what I would do is to, and I think, I'm pretty sure my slides have this. Basically, I can use this. My step 1 would be to get moles of CH3COOH. And then step number 2 is to get moles of NaOH from stoichiometry. I'll put stoich there. And then step number 4 is once I have step number 3. Step number 3, once I have moles, use moles and molarity, big M, to get volume. All right. So here's what that looks like. And we're going to stick with the millimoles so we don't have to mess with the whole 1,000 milliliters in 1 liter. So here we go. We have, for acetic acid, we have 35.0 milliliters. It's a molarity of 0.108 millimoles per milliliter. Giving yourself 3 sig figs, that means you have 3.78 millimoles of acetic acid. The next step was to use stoichiometry to get to millimoles of NaOH, which I know they're going to be the same because they react on a 1-to-1 basis. But you should show that because you never know. Stoichiometry could change up on you. Okay. So millimoles of NaOH would be, we'd piggyback from our 3.78 millimoles of CH3COOH. I usually put it over 1. And then from the coefficients in the balanced equation, I would put 1 mole of NaOH over, 1 mole of CH3COOH. And yes, that gives you 3.78 millimoles of NaOH that you need to get to the equivalence point. So now we use those millimoles and the molarity to get to volume. So it looks like this. 3.78 millimoles over 1. And the molarity, we have to use the flipped version of the molarity. So we have to use 1 milliliter over 0.235 millimoles. And giving ourselves 3 sig figs. You're looking at 16.1 milliliters. All right. So just kind of keep that in the back of your mind. Then we kind of finish up with kind of a little bit about indicators, I think. Oh, no, other titration curves than indicators. Okay. In this case, actually, the difference here is the analyte. So what's in your beaker is the base, and you're dripping in acid. So it's going to be an S-shaped curve, but it's kind of backwards. Yeah. Because your pH probe is going to see the base and you drip in acid. You're going to have a sharp change equivalence point, and then once you're beyond the equivalence point, it's going to be very acidic. So one of the ones we did not do was, what if you have a weak base and a strong acid? And we're going to have the weak base as the analyte, so that's what our pH probe is going to see first. So it's going to be basic, and then go acidic. And so you kind of see this sort of slopiness associated with your weak base, okay? And then you can see the equivalence point. And then this actually part of the curve is kind of like the curve we saw a minute ago, where you're dripping strong acid into a strong base.
So, I'm sorry, is the analyte the dripped in?
The analyte's the beaker.
Liquid, okay.
Yeah, the analyte's the beaker, and the titrant's in the burette. So another sort of twist on titrations is that what if we talked about polyprotic acids, H3PO4 actually, it looks like it has 3 hydrogens it can kick off. The first one kicks off to a high extent, and then the other 2 not so much. So we should be able to kind of see that on our titration curve. So what if we put phosphoric acid as our analyte and we dripped in sodium hydroxide? This is what it would look like. So you can kind of see this is the H3PO4, and it finally kicks off 1 proton, gives you H2PO4, and it kicks off another proton and gives you HPO4. So this is at least showing 2 of those 3 protonations, or deprotonations. So the last thing I want to talk about is indicators. So can you see here where you would want, we have things that change colors. Red cabbage changes colors. It has a spectrum of colors that changes depending upon the pH. Well, if you have something that changes colors around pH 4, that's going to help you catch this equivalence point. If you have something that changes pH around, between 8 and 10, the phenolphthalein, that liquid would be a good indicator. This liquid down here is methyl orange, it's an indicator, phenolphthalein. So it kind of depends on where your pH is going to change for your equivalence point as to what indicator you'll use. So these are different indicators. Phenolphthalein was the one we used in Chem 1. It goes from clear to pink, about a pH of 9. You're like, well, that's not neutral. Well, remember that that's when you guys with your HCl adding your NaOH, you hit that end point. It jumped up very quickly. So actually that works out well. But you would want to pick your indicator. why not just use red tabby? It's like totally cool with everything. So this is overlapping, showing you the strong S1, the orange one is the strong acid with the strong base, and then kind of this wimpy looking like one, this was the weak acid with the strong base. So this is what your two curves should look like. All right. Goodness, had time to spare. Let's start unit 5.
Alright.
So these problems aren't done yet, but so keep checking back, and my goal is to have them in my Sunday night posted. So I gotta do them and scan them and post them.
You're still doing Monday, right?
They're due Monday, yes. Jacob said, let's start. So, yeah, we'll just see what I want to do Monday, Wednesday. One of those days we got to do Unit 5, but if I can come up with some review things, I will.
It's gonna be a long weekend.
Yeah, chemistry sort of weekend. Yay!
My nephew, turns out, is brilliant with this stuff.
Thank you.
He's going up to, my sister got him in some private college up in northern Iowa. And he's like, oh, it's all